So now we are going to evaluate f prime z over fz dz over this curve C in a different way by using Cauchy residue theorem. So we have that fz is analytic except poles inside C. Okay, then fz may have also zeros inside C. Okay, so therefore, so the function fz by fz is analytic inside C except the zeros and poles of fz inside C. Okay, so now let fz has a zero of order m naught at z naught C. Okay, so then we know that fz can be written as z minus z naught to the power m naught, because it has a 0 of order m naught at z naught into zz, and we know that this where this function zz is analytic at z naught and z of z naught is not equal to 0. So now we want to have f prime z by fz. Okay, so what is the derivative of fz? So we have derivative of fz is m naught z minus z naught to the power m naught minus 1 cz, and plus the first function is z minus z naught to the power m naught, and second function derivative is g prime z. Okay, so therefore f prime z by fz, because f prime z is this one and fz is this one, so you divide f prime z by fz, this becomes m naught and z minus z naught plus g prime z and zz. And now you see that your zz is analytic at z naught, and which is not equal to 0. This is not equal to 0. So therefore this function is analytic at z naught. Okay, so this function is analytic at z naught. So therefore there is a Taylor's expansion about z naught, that means in powers of z minus z naught, non-negative powers of z minus z naught. So from here, from this you can see that f prime z by fz, this has a pole, because this is 1 by z minus z naught, and what is the coefficient? M naught. So your f prime z by fz has a simple pole. So has a simple pole at z naught, and with residue, and residue is nothing but the coefficient of 1 by z minus z naught, and there is nothing but m naught. So we have seen that if fz has a 0 at z naught of order m naught, then f prime z by fz has a simple pole at z naught with residue m naught. So, and in the theorem we have assumed that n is the total number of zeros of fz inside C counting multiplicities. So therefore f prime z by fz will have simple poles at those zeros, and what will be the residue? Residue will be the sum of those orders. So what is the total order? Total order number of zeros is n. Okay, so that you just remember. So similarly, so if fz has a pole of order say n naught at z naught, then in this case we can write fz equal to some phi z by z minus z naught power n naught, because z naught is a pole of order n naught. Alright, and where your phi z is what? Phi z is, you already know that this is analytic at z naught, and your phi of z naught is not equal to 0. Okay, so we again differentiate this. So what is the derivative of fz? So this is nothing but your minus n naught z minus z naught to the power n naught minus 1 and your phi z, and plus your phi prime z, because second function is phi z, and this is z minus z naught n. Hence again we see that f prime of z fz, from this you can see that this is n naught by z minus z naught plus your phi prime of z by phi z, where this function is analytic at z naught. Okay, so therefore it will again have a what, because it is analytic at z naught, so it has a Taylor series expansion about z naught, that means in powers of z minus z naught, non-negative powers. So you see that from here that f prime of z fz, this f prime z fz has a again a simple pole, because the only non-negative powers is z minus z naught to the power minus 1. Right, so this has a simple pole at z naught with residue. In this case the residue will be minus n naught, this minus n naught. Okay, so this is minus n naught, that means n naught was the order of the pole of fz. Now minus n naught is the residue of f prime z by fz at z naught. Okay, so and in that theorem we already had that p is the number of what? P is the number of poles. P is the number of poles of fz inside C. So on the other hand, n was the number of zeros of fz inside C. So therefore this f prime of z by fz, we have seen that this has simple poles at those singularities, and what is the residue? So residue is summation of the residues. So and in case of poles, the summation of residues is minus p, and in case of zeros it is n. So therefore by Cauchy residue theorem we will get that integration of f prime z fz over c dz will be twice pi I times sum of the residues. What is the sum of the residues? For zeros I got n, total zeros, minus p, because for poles we have seen that the residue is minus n naught. So for each pole we will get minus n naught, minus n1, etc. So that is minus p. So we have got this, and you just name it as b now. So what was a? A was nothing but the value of this contour integral evaluated by the other method, and that was, we got that I times the difference of argument of fz over c, over the same curve c. So this was a. So from a and b, if you equate, then you see that difference of argument of fz is equal to, so it is I cancels out, so twice pi n minus p, and that implies that 1 by twice pi, this difference of arguments of fz is equal to n minus p. So this is the argument principle. This is the statement of the argument principle. Okay, so that's all. Thank you.